Hi, I'm Stephanie Ho and I'm a postdoc at Texas A&M University. Here I'm going to share with you a recently published paper which analyzed the morphological and rotation structures of the circumgalactic magnesium-2 gas around low redshift galaxies in the EAGLE cosmological simulation. In particular, we show that the corotating magnesium-2 gas extends to far away from the galaxy center, but observational bias could lead observers to underestimate the radial extent of the corotating gas. The motivation of our study is our previous observational result, which showed that magnesium-2 gas around low redshift star-forming galaxies corotates the galaxy disk out to several tens of kiloparsecs from the galaxy center. This means that the cold CGM traced by magnesium-2 has significant angular momentum. However, because the CGM has very low gas density, and these observations are conducted through quasar sightlines, it is hard to map the distribution and the kinematics of the magnesium-2 gas around individual galaxies. For example, is the magnesium-2 gas isotropically distributed, or is the distribution axisymmetric? And how extended are these corotating gas structures are? These are questions that we're trying to address in this paper. On the right, we show a simulated galaxy example. We define the orientation of a galaxy using the stellar angular momentum vector, and we align the galaxy such that the right-hand side corresponds to the redshifted side of the stellar rotation. The left and right-hand column shows the same galaxy, but projected edge-on and face-on. The top row shows the magnesium-2 column density map. Clearly, the magnesium-2 gas distribution is not isotropic, but is somewhat disky. The bottom row shows the line of sight velocity map. Blue color means the gas is moving towards us, therefore it's blue shifted. Red color means the gas is moving away from us, therefore it's red shifted. We see a blue shifted and red shifted side, which is an indication of rotation. Also, because the magnesium-2 gas at the right-hand side is red shifted, it means that the magnesium-2 gas corotates with the stellar component of this galaxy. While this is a single galaxy example, let's look at stacks of galaxies. Here, the color map shows the fraction of galaxies in each stack with corotating magnesium-2 gas, and the magnesium-2 gas has high enough column density to be detected. Different columns shows results from different stellar mass bins, and different rows shows galaxies projected at different inclination angle. From the shape of the contour, we clearly see that the corotating magnesium-2 gas is not isotropically distributed, but has an axisymmetric structure. Also, the corotating magnesium-2 gas is more extended near the galaxy major axis, which is the horizontal axis of the plot, but is less extended near the galaxy minor axis, which is the vertical axis of the plot. Then let's look at the 1D profile. The horizontal axis shows the impact parameter, and the vertical axis shows the fraction of detectable magnesium-2 that is corotating. So if the gas is moving randomly, then we expect this fraction to be 0.5, because there would be an equal chance for us to detect rotating and non-rotating gas. Again, different columns shows results from different stellar mass bins. First, let's focus on the solid lines, which shows the results for the magnesium-2 gas within the virial radius of individual galaxies. Darker color lines means regions closer to the galaxy major axis, and the lighter color lines means regions closer to the galaxy minor axis. We see the darker lines lies above the lighter lines, which reiterate the results that corotating magnesium-2 gas is more likely to be detected near the galaxy major axis. And we see that it's possible to find corotating magnesium-2 gas out to 100 kiloparsec or even further. However, observers do not know where the gas lies along the sightline. Therefore, instead of selecting magnesium-2 gas within the virial radius of individual galaxies, it is typical to select the magnesium-2 gas using a line of sight velocity window, for example, plus or minus 500 km per second. And we show the result using the dashed lines. Especially in the lower mass bin, we see that the dashed line lies below the solid lines, which means that the magnesium-2 gas outside of the virial radius but selected by a line of sight velocity window actually contaminates the corotation signal and make observers less likely to determine the gas at large impact parameter to be corotating. Therefore, this means that observers could be underestimating the radial extent of the corotating gas. Feel free to check the paper for results that I did not mention here, for example, how a result depends on the galaxy stellar mass and differs between star-forming and quiescent galaxies. Thank you.